Log on, tune in, find out. Another good idea from Cambridge.
Laplacian is multiplied by epsilon square, and in the following I shall be interested in particular in the case where epsilon is a small parameter called the semi-classical parameter. You can think of epsilon as some kind of ratio of, say, a macroscopic scale to a microscopic scale. Okay, so basically this implies that both variables, space and time, are on the fast epsilon, are to be seen on the fast epsilon scale. But there is another function in the game which I assume to be given, which is this function v of x, which basically describes or represents the potential field within which the quantistic particle whose motion you're interested in tracking is moving. Okay, so for the following, v of x is going to be a scalar real valued potential function. Okay, now, well, yeah, and there's of course, I mean, we have a first order time derivative, we need one initial data. Now, well, you could say this is a linear partial differential equation. We all know about mathematics of the 60s, early 70s, semigroup theory. You just use your classical semigroup results, and that's it, and that solves the problem. True and not true. Why? Well, in particular, well, if you're interested in physics, or if you're interested in what physicists are interested in, which is not completely the same thing, then actually you have to do more. You have to do a quadratic post-processing job on the equation. So in particular, when you want to compute observables, physical observables, or densities of observables, you have to compute quadratic quantities of the wave function. So in particular, maybe the most basic physical observable is just the probabilistic position density of the particle that you are tracking, and this is computed by taking the wave function, its absolute value, complex absolute value, and squaring it. Another observable would be the current or the flux density vector, which is computed by taking the first order, taking the gradient, the spatial gradient of the wave function, multiplying by the complex conjugate of the wave function, taking the imaginary part, and for a good measure, rescaling by epsilon. So you see also this is a quadratic quantity in the wave function. Energy density likewise. So it means essentially you have to solve your linear equation, and then you have to do a quadratic post-processing job on it. Okay, now I shall be interested in computing in various ways the high frequency limit as epsilon tends to 0 of the observables. And the reason for saying of the observables basically is that computing the limit as epsilon tends to 0 of the wave function is just a meaningless exercise. And why is that so? Well, there's a problem here. Typically, u epsilon, the sequence of solutions, converges to a limit, u0, only weakly. And the reason for this is that the Schrödinger equation propagates oscillations of wavelength epsilon in space and time. Okay? And of course, weak convergence, as we all know, does not commute with quadratically nonlinear operations. So you have a problem there. So for example, here you just see a plot. Here this should be of a numerical simulation. This should be the x-axis, one-dimensional. This is time, and we start, well, what you see here actually is the position density. Initially is a Gaussian, but then what you see here as time develops, oscillations in space and time occur. And this is just the basic problem that we have at hand here. Okay, for the following, let me make a few assumptions. Let me, for the sake of simplicity, assume that the potential is smooth and bounded from below. Very basic assumption, and this applies among, it also applies many other things, but in particular it implies that the Hamiltonian operator is essentially self-adjoint on L2. Assumption 2 is I assume that I have uniformly bounded conserved quantities, in particular the initial at time t equals 0, in particular the initial mass and the energy. So this is just an assumption that I shall use for the rest of the lecture. Now we all know about Stone's theorem. This is what I meant referring to semigroup group theory. Basically says that I times the Hamiltonian generates a strongly continuous group of unitary operators on L2, and this in particular means that the position density is an L1 conserved quantity in time. Okay. Now, I mean, in a similar way, you also prove that this quantity is conserved energy. Yeah? Okay. So, what does this imply? This implies that after extraction of a subsequence, there is a limit of the sequence of position densities, which I call N0, and this is, of course, in general a measure, and the limit process, say, holds in measure weak star. So the job here at hand is to identify N0. Okay, now, of course, you can play exactly the same game in momentum space. So basically, compute the momentum density. For this, you have to take the wave function, you have to Fourier transform it, you have to rescale here by epsilon, take the absolute value square, and then rescale by epsilon to the nth power just to get a good norm in L2, or in L1 actually. Now again, this is an L1 conserved quantity, so by the same reasoning, there is an M star and M plus weak star limit, which I call P0, and the question is identify P0. So now we have a game in position space, we have a game in momentum space. That basically means we are in phase space, right? So we can play a general game in phase space. So that means we have to set up a so-called general observables, and they are just they are actually given by phase space functions, which I assume to be real valued, phase space, position, momentum space, so they are real valued functions. And then from them, I compute the corresponding Weil quantization. Now, what is the Weil quantization? Well, I'm not going to write it down. The Weil quantization is just a particular way of quantizing a function, a phase space function, which is just, in some sense, it's in between the left and the right quantization, or the left symbol and the right pseudo-differential symbol. And it has a very nice property. So, once you have the observable operator, you can, of course, define the average value of the observable A in the state U epsilon being the wave function. And all you need to do for this is just compute the scalar product of the application of the observable operator to the wave function with the wave function itself. Okay, again, this is a very general quadratic function now in the wave function. And the limit, well, the physical problem of semi-classical calculus is to find all those limits of average values of observables for a very large, for the largest possible set of observable defining functions A. Okay, so that's the job at hand, and this is clearly a generalization of what I told you before of position space and momentum space. Now there is a extremely well-known tool, and that is the Wigner transform, and the Wigner transform in fact facilitates the computations that I'm going to show you. Basically it is the following: take a temper distribution even, okay, on Rm, which I call f, and this is very important, and also choose a scale of positive numbers epsilon which tend to 0. Okay, then the Wigner transform of f on the scale epsilon will be a phase space function already. It will be quadratic in the distribution f, and it is set up in this particular, somewhat odd-looking way. Now, what do you have to do in order to compute the Wigner transform? Well, first you take f and compute its tensor product by its complex conjugate. Now, keep in mind, when you compute the tensor product of a distribution with another distribution, you basically already double dimension. This already, philosophically speaking, morally speaking, takes you into phase space. Okay, and then what you do is just a linear coordinate transformation, which you see in here. Okay, and as a third step, you throw in a Fourier transform with respect to the shifted variable here. Now, instead of explaining to you why this setup, I just want to show you what it does. Okay, and in particular, what it does is this here. It shows you, actually a very simple computation shows you that you can compute average values of observables by just taking the Wigner transform and integrating against the observable defining phase space function. So what does that mean? You have taken a quadratically nonlinear job and you've transformed it into a linear job. Well, you pay a price for it, and the price you pay is doubling dimension, right? Now, what is the trick? The trick is, of course, that the quadratic nonlinearity is already in the transformation that you apply. Okay, but still, I think it's a very, very nice and very, very good trick. Now, another proposition, which is also very easy to prove, says that now, if f is not only a sequence of tempered distribution, but if f, say, are functions which lie in a bounded subset of L2, then when you compute the corresponding Wigner transforms, then it will be, what comes out is uniformly bounded in the space S prime. Okay, in the space of tempered distributions on phase space. That's actually very easy and straightforward to prove. Now, what does that imply? That means basically if you take a sequence of L2 functions which are uniformly bounded in L2 as epsilon tends to 0, then by weak compactness, after of course extracting a subsequence epsilon k, there exists a tempered distribution W0, which is the weak limit of the Wigner transforms of your subsequence. Okay. Now, this is a tempered distribution, but actually it has many more properties. And a very important property is that you can prove by an additional effort, actually, that W0, the weak limit, is a positive measure on phase space. And this is actually sort of striking, because when you look at Wigner transforms themselves, you can find out also rather easily that generically speaking, they change sign. They change sign through oscillations, and there's actually basically only one case of wave functions which generate a Wigner transform which is uniformly positive on phase space. That is Gaussian. Not very interesting, right? But, as I said, by working on it some more, you prove that the limit of that highly oscillatory sequence of sign-changing functions converges to a positive measure. Now, if you go into physics, then basically you realize that this is nothing else but the manifestation of Heisenberg's uncertainty principle. Actually, by Heisenberg's uncertainty principle, you can use it to exclude the fact that generically the Wigner transforms don't change signs. Okay, now a very simple proposition is the consequence. Take a sequence of uniformly bounded L2 functions and take an observable defining function, say, in the Schwarz space S. Then when you want to compute the limit of the average values of the observable in the state f epsilon, all you need to do is take the Wigner measure, the limiting Wigner measure. Take the test function and integrate it against the limiting Wigner measure. So basically, in order to solve the semi-classical problem of quantum mechanics, all you need to do is you need to find out what is the Wigner measure associated to the solution of the Schrödinger equation. That's a very well-known exercise, so let me repeat this. Take the Schrödinger equation, the initial value problem for it, of course. Compute the Wigner transform of the wave function at time t, which will be a time parameterized phase space function, of course. Then, by what I said, this will converge to a weak limit, which I call W0 of t. The average values of observables will converge to the corresponding linear functionals, and actually this convergence is locally uniform in time. So the only job that remains to be done is compute or identify W0. And there is a result, a proposition which I would say is folklore of the 80s or something, which says basically that W0 satisfies a linear transport Liouville equation. And the transport Liouville equation is just a linear partial differential equation whose characteristics happen to be the Newtonian ODEs. And this is precisely what Planck meant in the year 1900 when he said that classical mechanics is the limit as h bar tends to 0 of quantum mechanics. Okay. Idris.
There was passing to subsequences. Suddenly now you're telling me that the limit is a solution of this equation.
Yes.
All the limits, or there is a unique limit, or?
This is, of course, a very good question. If you take a sequence of L2 functions, there is no way to guarantee that there will only be one Wigner measure associated to it. But the only source of non-uniqueness here is through the initial data. So basically, you compute your initial Wigner transform, pass to the limit subsequence-wise, fix the subsequence, and for the same subsequence, you will get the limit for all times by solving the equation. That's a very important point, actually. Okay, so, now of course you also want to pass to the limit in the densities. For example, under the assumptions that I made, you can exchange momentum or velocity integration with a limit process. You can compute the limiting position density by just integrating out the momentum coordinate from the Wigner measure, and you can compute the limiting flux density by just computing the first order moment of the Wigner measure with respect to momentum. Now, if additionally you prove if the initial position densities form a tight sequence as epsilon tends to 0, then you can exchange also a limit process with a double integration over all phase space. Okay. But all this is very well known. It just serves me as a lengthy introduction. Just to give a few references in this, phase space analysis of the high frequency limit of the linear Schrödinger equation basically already appears in the year 74, maybe even before that. Work by Schnirelmann, Patrick Gérard in the 90s. There's an important paper by Pierre-Louis Lyons and Thierry Paul in the year 93, and then there's our paper, which appeared in the year 97. And all this is, of course, based on work by Eugene Wigner of the year 1932. Okay, Bohmian mechanics. What is Bohmian mechanics? Bohmian mechanics is something extremely simple. Just compute the quantistic velocity field. How do you do this? Well, you compute the quantistic position density divided by the quantistic flux density divided by the quantistic position density, and this is what we call the quantistic velocity field. Or if you want to write it in terms of wave functions, it looks like this. Now, it looks kind of ugly, right? You have this, the wave function in the denominator, so you will have to worry about singularities, nodes of the wave function, and so on. Anyway, now just if you want to know what the Eulerian viewpoint of Bohmian mechanics is, all you need to do is solve that system of ordinary differential equations in position space. So on the right, the vector field defining the ODEs is precisely the quantistic velocity field. Now you can say, well, there's a problem here, right? I mean, there's a regularity problem. What happens when the wave function hits 0? Well, there's a theorem, and I think it's a really nice theorem proven by Berndl et co-authors in the year 95. And the theorem basically says that the flux associated to this, or the Eulerian Bohmian flux, if you want, exists globally in time, but almost everywhere relative to the initial position density measure. Okay, and is of course smooth on its maximal domain of definition. So this is actually very, very, in some sense, I think it's a deep theorem. Well, I mean, if we all had our training in ODEs, so we could also think of just applying ODE theory. Well, even if the wave function is as smooth as it needs to be, as you want it, there will be problems with zeros here, right? So in general, this velocity field will not be Lipschitz in X. So classical theory goes down the drain. It will not be in W11, so Lyons-Di Perna theory for ODEs goes down the drain. And it also will not be BV. So Ambrosio theory goes down the drain. So you need to have something completely different, and the completely different thing is here. Yeah, the proof is actually not really difficult once you have the idea. Yeah. Okay, now moreover, there's also a moreover to this, and the moreover is that at any time t, you can compute the position density as the push forward of the initial position density through the Bohmian vector field, through the Bohmian flow. Okay? And this also implies that the position density is a weak solution of this classical mechanics continuity equation, if you want. Now, I mean, this is the Eulerian viewpoint of Bohmian mechanics, and I really think it's kind of maybe philosophically interesting, and when you browse the internet, you can come across many, many sites where the philosophy of Bohmian mechanics is discussed. I'm not going to go into this. I just try to do some mathematics on it. I leave the physical, philosophical considerations and conclusions to others. Now, I think in some sense, mathematically, this is sort of an endpoint unless you go to the Lagrangian formulation. Now, what does it mean, Lagrangian? Well, it basically means take Eulerian and differentiate with respect to time. Okay? And what you get is this equation here, this equation here, by just differentiating along characteristics, and sort of you need to do something with the right-hand side. Well, but there are the so-called Madelung equations of quantum mechanics, which you find on page 5 to 7 of every good book of quantum mechanics, maybe 10, but not further down the road. And these are just the fluid equations which you derive from the Schrödinger equation. So the first equation is just the continuity equation that we had here, and the second equation, well, it looks sort of like an Euler equation with, if you want, an internal complicated looking pressure term. Okay, and here again I should say that this is no ansatz, nothing, this is just an exact computation. So when you go Lagrangian in Bohmian flow, all you need to do is you replace the right-hand side here by these two terms, right? And suddenly what do you get? And then what you get is a system of phase space ODEs, which sort of resembles the Newtonian ODEs, except that there is an ugly guy up there, and this is the so-called Bohm potential. And you see this is the definition of the Bohm potential here. Okay, well, ODEs, it's not even ODEs, right? Because, I mean, you need to know this position density. Now, if you argue formally for a moment, then what you see here is that this problem is just an order epsilon square perturbation of the Newtonian ODEs. But really not all is well in Bohmland because because of the highly oscillatory nature of the wave function. This term can actually be, this term here can actually be order 1 over epsilon. Okay, so yeah, and of course it's highly singular in the nodes of the wave function. So there is a problem, but it looks sort of intriguing, and the intriguing fact is, as I said, the Lagrangian Bohmian equation of formal order epsilon square perturbations of Newtonian LDs. Okay, now this sort of leads me to a definition, and this is the definition of Bohmian measures. And let me just not tell you why I do this at the moment. Let me give you the definition and then show you what it does. Okay, so given a scale of positive numbers, epsilon that tends to 0, given a wave function, say in H1 on Rm, I can of course compute the position density and I can compute the flux density, and both are going to be L1 functions. Now I set up a measure, a positive measure on phase space, which I call the Bohmian measure, and the Bohmian measure beta epsilon will also depend on the scale epsilon, obviously, and it's just a monokinetic measure which is supported on the graph of the quantistic velocity field, and whose strength is given by the position density. Okay, so this is a positive measure on phase space, and you immediately convince yourself that the zeroth and first order moment of it with respect to the momentum coordinate are the correct ones. That is position density and flux density. Now, well, you could go on computing moments, for example, compute energy density, by the kinetic one. And then you see that, well, it's not really the right thing that you get, because you miss one term here. Okay, so what I'm trying to say with this is that the Bohmian measure does not give you all the moments correct. Okay, nevertheless, it does an interesting job. Now, assume take for a moment the wave function u epsilon as the solution of the Schrödinger initial value problem. and compute the Bohmian measure associated to u epsilon. So this is going to be a positive phase space measure with being parameterized in time t. And of course, at time t equals 0, I can do the same thing. Now, there's a simple proposition that you can prove, and the proposition is that beta epsilon of t is the push forward of the initial Bohmian measure with respect to the Lagrangian Bohmian phase space flow. Okay. And this Lagrangian Bohmian phase space flow is defined almost everywhere with respect to the initial Bohmian measure. And that's actually an extremely simple consequence of Bernoulli's theorem. You just have to look at it in the right way. And in particular, what you show using this and some other little estimate is that the Bohmian measure solves a Vlasov type equation. And somewhat unpleasant Vlasov type equation, because in the Vlasov type equation, you have the Bohmian potential term entering, which, I recall for you, depends on the position density. Okay, so you have to close this equation by defining an epsilon as the integral of beta epsilon d psi. Okay, but the interesting thing is that this Bohmian measure sort of its structure remains invariant through the propagation of this equation. So you have a Vlasov equation for the Bohmian measure. The Vlasov equation is, again, formally an order epsilon square perturbation of the equation which is satisfied by the Wigner measure, which is the right one, as we know. Now, as probably some of you know, there has been a long quest for rewriting quantum mechanics in an optimal transportation framework. And what I'm saying is that this could be a beginning of it if you combine the theory by Ambrosio and others on optimal transport methods for Hamiltonian systems, and if you combine this with the work done by Savary and others on the quantum drift diffusion equation. Because in the quantum drift diffusion equation you have exactly this ugly singular term entering, but of course in a nicer, that is in a diffusive framework, while here you have a Hamiltonian framework. Okay. And of course also you could use this as a basis for numerical investigations. And actually, if you check the literature, the computation of Bohmian trajectories has been extremely popular with chemists and physicists. Okay. So what does the Bohmian measure do? The Bohmian measure encodes the full quantum mechanical information contained in the position density and the flux density, and it evolves through the Bohmian Lagrangian flow. So sort of, it's kind of very, here it looks very intriguing to analyze the limit as epsilon tends to 0 of the Bohmian measure, and in particular, it looks very intriguing to compare that limit to the Wigner measure. Okay. Now, well, there's a simple proposition which says that if you take a sequence of wave functions which is bounded uniformly in L2, then up to extraction of subsequences, the sequence of Bohmian measures will converge to, of course, a positive limit measure. Now, furthermore, if you have the usual bounds, then you can, as in the case of the Wigner measure, you can exchange integration, velocity or momentum integration with the limit process in the 0th and first order moments, and you get the right things. Okay. Now, additionally, just again, as in the case of the limit of the Wigner measure, if an epsilon is a tight sequence, then you can exchange limit process and double integration. Okay. So that's very simple. Now, as I said, what I want to do is compare the limiting Bohmian measure to the sequence of Wigner, to the Wigner measure, W0, associated, of course, to the same sequence of wave functions. Now, it turns out that a theory, a pretty well-developed theory, is rather convenient for that, and that's the theory of Young measures. Just for those of you who don't know what the Young measures are, just a short definition. If you are given a sequence of measurable functions, say measurable vector fields defined on Rm with values in Rn, then there exists a map, mu sub x, which is called the Young measure associated to f epsilon, such that first of all the Young measure is weakly measurable in this sense here, and then this is the most important point, you can use the Young measure to compute weak limits of nonlinear functions of the sequence by just integrating the nonlinearity against the Young measure. This is essentially what this line says. Of course, you have to be careful with the choice of the nonlinearities. Here I have only assumed that the sequence of functions f is measurable. I haven't assumed any uniform bounds, so here I need to restrict to C0 test functions. If you have uniform bounds, you can admit the larger class of test functions, of course. Now, why is that adequate for the Bohmian measure? Well, think of the Bohmian measure applied to a test function. If you apply the Bohmian measure to a phase-space test function, you will get an integral like this. Okay, and this can of course be, well, and the limit of this can of course be expressed in terms of the Young measure, which is associated to the sequence consisting of position density and flux density, right? And there's a very straightforward consequence which basically says that, well, first of all, it gives you a lower bound on the limiting on the limiting Bohmian measure, which can be just computed in a straightforward way from, as I said, the Young measure associated to the sequence. And additionally, if the sequence n epsilon converges to n0 and L1 weakly, then you have an equal sign here. And the reason for this is simply that Young measures deal very well with oscillations, but they don't deal well with concentrations. Okay, and this is the price that you have to pay. All right, a few consequences. Well, first, proposition on being monokinetic. In kinetic theory, it's always very important to check whether a measure which satisfies, say, a Vlasov equation is monokinetic or not, because then you can write your Euler equations and so on without closure and so on. Now, here is a result. Now, if the sequence of position densities converges in L1 strongly, and if the sequence of momentum density or flux densities converges in measure, okay, then the limiting Bohmian measure is already a monokinetic. And of course, the in measure limit of the flux density is equal to the weak measure limit of the same sequence. Now, what you would really like to have is the other direction, but the other direction, unfortunately, is not completely true. Okay, now, many people have been interested in what happens to the Bohmian Lagrangian trajectories themselves in the limit process as epsilon tends to 0. Okay. Now, there is a connection between the limiting Bohmian measure and the Young measure associated to the Lagrangian Bohmian trajectories. And the connection is given here. Essentially what it says is that where you have to integrate out one variable here. But if this was an arbitrary test function, it of course would mean that you could compute a gamma tx from beta 0. But this is not an arbitrary test function. This is the fixed initial position density. So it means you sort of lose some information here, which is sort of, and the loss of information is sort of conveyed by this one integration that you do. So the message here is that if I'm given the Young measure of the Lagrangian Bohmian trajectories, then I can compute the limiting Bohmian measure. Not quite the other way around. Okay, but keep in mind, of course, asking to know the Young measure of a sequence is really asking a lot. It's much, much more than asking weak limits or something. It basically means that you need to know all the scales of oscillation which are present in the sequence. Okay. All right, now for the following, let me assume that the sequence of wave functions is given in WKB form. Well, and what I mean is just to write the sequence of wave functions in its, say, radial representation and just rescale the phase by epsilon. Okay. Now, two theorems. First result basically says that, again, assume that U epsilon is uniformly bounded in L2 with uniformly bounded kinetic energy. then if you have two assumptions, the first assumption is n epsilon converges to n0 strongly, so the sequence of position densities assumes a strong L1 limit, and now I put this under quotation marks because I don't want to formulate it very precisely. If the quantistic velocity field converges uniformly to a limit, then the limiting Bohm measure is equal to the Wigner measure is equal to the monokinetic. Now, again, we cannot go into the other direction here. Okay. You might want to ask another question. You might want to ask the question, under what conditions can you guarantee that the limiting Bohmian measure is equal to the Wigner measure without assuming that both are monokinetic? Well, in cases other than where both are monokinetic. And there's a theorem. And the theorem says the following, and I'm going sort of to give you the spirit of these assumptions here. And the spirit is, if the gradient of the square root of the position, if the square root of the position density oscillates on scales which are larger than epsilon, and if the quantistic velocity field also oscillates on scales which are larger than epsilon, then the limiting Wigner measure is equal to the limiting Bohmian measure. Again, the question is, can you go the other way? And the answer is almost. And you sort of can quantify what the almost here means. Okay, but I'm not going to go into it. Okay, let me give you a few examples. Let me begin with a sequence of what you might want to call oscillatory functions. And what are those? They are just periodic. Well, I assume they are periodics. Periodics with a period of the order of epsilon, modulated by a smooth test function. Okay? So G would be a function which is say smooth and periodic on some lattice L, which is an order 1 lattice, and then of course you rescale here by epsilon. Now, what you can prove here is that the limiting Bohmian measure is equal to the Wigner measure if and only if G carries only a single oscillation. So that means basically if G is a harmonic. Okay? So this is if and only if. So basically what does that mean? I mean, for those who have some experience in semi-classics, it basically means that after caustics, where essentially the wave function consists sort of a superposition of many harmonic type functions, you will have a problem. Okay, sequence of concentrating functions. And when I say concentrating functions, what I mean is not that the sequence of functions itself concentrates, but the corresponding position density. So the square of the modulus. So assume that U epsilon is of this form here, m being the dimension, concentration should happen at x0. That of course implies that like the integral of f squared is 1 or something, that implies that the corresponding position density converges to a delta centered at x0. Okay. Now, proposition, well, the conclusion is that the limiting Bohmian measure is equal to the Wigner measure if and only if f is 0. This is another bad news, right? I mean, this is also something that could happen at caustics. So you see, I'm collecting bad evidence here. Okay, now comes the good evidence, actually. This is a semi-classical wave packets, coherent states. Keep in mind, well, this is a general form of a coherent state. Keep in mind that those are sequences of functions which concentrate, but on the scale square root of epsilon, not on the scale epsilon. So on the scale much larger than epsilon. Okay. Now here, this is actually a case where the Wigner measure is equal to the limiting Bohmian measure. And this has actually been used in a recent work where the authors showed that you can really compute the limits of Bohmian trajectories in the case that the initial data are prepared in a very, very precise way through coherence. Okay, another example, eigenfunctions. Well, for the sake of simplicity, consider the harmonic oscillator. Okay, now consider the associated spectral problem. which you of course can solve exactly, and you have the sequence of eigenvalues, and just let me fix a sequence of eigenfunctions which is normalized in L2. And of course let me assume that the eigenfunction, well of course the eigenfunctions can be chosen real valued here. Now choose a sequence epsilon L which tends to 0 such that the corresponding sequence of eigenvalues converges to a positive constant, capital lambda. And you can do this. You can convince yourself that you can do this. Then what you can prove is that W0, the Wigner measure associated to the sequence of eigenstates, is the equiconcentrated measure on the energy sphere given by capital lambda. Okay? And there is, of course, much more general results for other potentials, quantum chaos, and so on. Now, for this case, we can compute the limiting Bohmian measure, and you see it is different if lambda is not equal to 0. Okay. All right. Now, WKB approximation. What is WKB? WKB basically means that if I choose the wave function at time t equals 0 in its WKB form with position density and phase independent of epsilon. Okay, well, it could be a bit more general, but let me say independent of epsilon, so Ni and Si are real valued and smooth functions. Then sort of you can compute an approximation to the wave function by solving the Hamilton-Jacobi equation, whose Hamiltonian is just the iconal term, or whose Hamiltonian, if you want, is the symbol of the Schrödinger operator. Then you need to solve the linear continuity equation, whose velocity field is given by the gradient of the phase. Now there's just one small problem with it, and the problem is that, as you all know, Hamilton-Jacobi equations as fully nonlinear equations in general develop singularities in finite time. So that means, in general, even after a finite time, there will be singularities which are transported into this quantity n0. And then you have a problem. Now there's a theory by Joe Keller, Peter Lax, and others from the 50s and 60s, which basically says that before the development of singularities of the Hamilton-Jacobi equation, that is before caustic onset, before the caustic onset time of the Hamilton-Jacobi solution S0, you can approximate the wave function through the solution of the Hamilton-Jacobi continuity equation, and actually the approximation is accurate order epsilon in L2. Now, if you want to know what happens after caustics, the situation is very complicated, and this works by Maslov, phase shifts, and so on and so on. Anyway, what can we conclude here? Now, there's one proposition that I have to offer, and the proposition is the following. Well, before caustics, we can prove that the Wigner measure associated to the sequence of wave functions is equal to the limiting Bohmian measure and is, of course, monokinetic. Okay, this is before caustic onset time. Now, structurally speaking, what happens at and after caustic onset? Well, after caustic onset, basically you can think of the wave function as a superposition of WKB states. Okay, let me take a superposition of two WKB states. Okay, well, of course, here the gradient of S1 is different from the gradient of S2 to make it really 2. Now, then you can compute in a rather simple way the limiting Wigner measure. And the limiting Wigner measure is just the sum of two monokinetics. So in particular, that means that the support of the limiting Wigner measure in phase space is just the union of the two velocity fields, or of the graphs of the velocity fields. Okay, let me do this exercise for the Bohmian measure. Now, if you do this, well, you have to work a bit. Yeah, it's a computation, but it's very simple actually. But in the end, when you compute the limiting Bohmian measure, what you see is that you essentially get an integral. You get an integral over monokinetics, but by integrating out this variable theta, which is the angle variable, you of course realize that the support of this is completely different from the support of the Wigner measure that I've just shown you. So basically, this means that beta 0 in this case is different from W0. Okay, so the conjecture that we have, and this is actually a theorem that we are trying to prove is that after caustic onset in generic cases, beta 0 is going to be different from W0. Okay, now, and you are, of course, welcome to draw your own conclusions about what that means for Bohmian mechanics. Okay, thank you very much.
Thank you very much. Other questions? Yeah.
Do you have anything similar for the...
Sorry, say again?
Do you have anything similar for the Dirac equation?
Haven't looked at it, but also for the Dirac, equation, Bernoulli's theorem, of course, applies even easier than Schrödinger, and you can prove that the Eulerian flow exists again almost everywhere with respect to the initial position density, and you can do the same basically. And what you get is probably simpler than for Schrödinger, because you have a first order operator. But we didn't do it. That's a good point actually.
Another question? No? Thank you once more.